So I'm going to spend the next few minutes just talking about one of the examples we looked at in this paper, particularly looking at the concept of the all-electric aircraft, let's call it that. So looking at power electronics as the enabler for allowing us to fly aircraft using electrical power. We'll talk a little bit more about why we might want to do that in a moment. So Power Electronics Research Group at Nottingham University does power electronics and electrical machines. I've included this slide really to say that this is not about the work of one person. This is about the work of a lot of people. One of the things we always notice about work in this area is it's very multidisciplinary. You need people who have lots of different understandings of different technology areas. So it's not the work of one person or one professor. Professors are good, but not that good. So it's coming together of, as we'll see, of electrical machine technology, the power electronics, and the electrical system that enables us to consider these types of electric flight. So let's have a look at the electric aircraft and look at why we're considering electric flight rather than continuing to use the gas turbines. This is a very often quoted diagram, which really says about how the industry and the regulators are looking at aviation. This particular chart is CO2 emissions from aviation, and the aviation industry is looking to get the CO2 emissions from flight down to 50% of their 2010 levels by 2050. Now, if we didn't do anything, if we'd stayed with the technology we had in 2010, then the CO2 emissions would more than double. So quite a big goal to reduce it by a factor of 4 over that time. One of the things you have to remember is that aircraft last 25 to 30 years. So the aircraft bought today will still be flying in the 2040s. So there's a long lead time in this as well. And so the good news is that we've done a lot of work already. Those green areas on there are areas of technology, operations and infrastructure where we've already made CO2 emission savings. The blue area is the additional technologies that we need to work on, and electrification certainly forms part of that. So if we take the idea that we might go to electric propulsion systems and we look at the size of motors we need to be able to do that, so I'm just considering the propulsion at the moment, not where the energy comes from, then small urban mobility aircraft, we already have the motor technology for that. We're beginning to see the demonstrators. When we move up into sub-regional and regional aircraft in the 1 to 5 megawatts, 1 to 10 megawatt range, then we're looking a little bit further out, but those are becoming possible. We're looking at large twin-aisled aircraft. We're looking at 10, 20 megawatts per wing of electric propulsion. And as you can see on that chart there, the timeline is even further out, looking at 2040, 2045. The other thing you can see on that chart is the motors that we've designed and built at Nottingham University, along with the power electronics that enable them. There's plenty of other demonstrators around. It's just easier for me to get pictures from my own team. And you can see there that we're a long way ahead of the curve needed for the aircraft. That's the way it has to be. The larger the aircraft, the longer the development period. And they won't develop an aircraft unless there's known technology. So it's good that we're now up to about 4 megawatts, about the size of machine that we need for a regional aircraft. Where are we with these technologies? Well, in terms of lifetime and efficiency, we're about at the level we need to be. Power density, volumetric density could do some slight improvements, and cost at the moment we're far too expensive. So There's a lot of work in manufacturing out some of the cost in these systems. Come back to that. When I'm talking about electric aircraft propulsion, I'm talking about having an electric motor on the wing that drives the aircraft forwards through the air. That motor would typically be controlled with a power electronic converter. In fact, it has to be in just about every case. We're not looking at necessarily going to battery-powered aircraft straight away. The example on the right there still has a gas turbine, but that gas turbine would be in line with the passengers in the body of the aircraft, driving a generator, going through a power converter to create a high voltage DC bus. That DC bus would then go out to the power converters that drive the electric motors on the wing to drive the aircraft forward through the air. By doing that, we save in three different ways. The gas turbine is no longer presenting a big wind resistance on the wing of the aircraft because it's now behind the people or the cargo inside the aircraft. The gas turbine only needs to spin at one speed and one operating point. So we can make the gas turbine far more efficient because it's only ever going to have to operate at that one operating point. It's not got to go into a high power mode for takeoff or anything like that. And the other advantage is that I've removed a lot of weight from the wing of the aircraft, and therefore we can reduce the structure around the wing of the aircraft and make the wings lighter and thinner. And you'll have seen this in some of the announcements from companies like Airbus and Boeing when they're talking about thin wing technology, trying to make those wings thinner, more efficient, and more effective. So a lot of ways in which we'll save energy even if we can't have battery powered aircraft. Now, when we look at that and we look at the enabling technologies, this slide is focused on electrical machines, but we're thinking about power electronics. But when we look at the electrical machines that we might use and look at the technologies, we find things like cooling, the way we do the windings, maybe advanced techniques in manufacturing and new materials. But we also find power electronics, the introduction of silicon carbide devices, the big increase we've had in available switching frequencies, and what that does for the excitation frequency of the machine is all part of this picture that has allowed electrical machines and power electronics in these applications to become a lot smaller and a lot lighter, and to make the whole concept of electric propulsion for flight feasible. When we look at the impact that some of these technologies might have against technology readiness level, so technology readiness levels when we're low down that scale, they're crazy ideas that are very futuristic. When we get to the right-hand side of that scale, like the magnetic materials, these are technologies that we could use today. And you see there that the biggest circle on that chart is actually wide bandgap semiconductor devices, the power electronics. And this chart is not looking at power electronics, it's looking at electrical machines. But power electronics is going to be the single biggest change in the size and the weight of electrical machines for quite a long time, because we can use these higher excitation frequencies, we can use higher voltages, and we can do that without creating significant extra loss because of the wide bandgap semiconductor devices. So have to remember that. When we look at what this means for different electrical machines, obviously the faster an electrical motor goes, the smaller it gets. And we've been predicting what's going to happen over time. What's happened in the last 4 years, what's going to happen in the next 10 years. And the fact that electrical motors are going to get increasing power density across the board. This only goes up to 20,000 RPM. When you start getting up above 100,000 RPM, actually the reverse can be true. But in the frequencies and the speeds we're looking at for aircraft, it's certainly true that the faster we go, the smaller the machine, and power electronics is enabling that to happen, as long as that doesn't make things like the gearbox or the propeller too large. When we look at power electronic converters, so this is about the power electronics we're going to use, one thing you always find is there's lots of different power converter topologies out there. When you read papers about them, you'll always find the authors saying that their power converter has a lot of advantages, and that's true. As we'll see in a moment, the different power converter topologies have different characteristics, and one of the important things is to match those to a particular application and a particular load profile. The other big thing that's happened, as I said before, is the introduction of wide bandgap semiconductors, silicon carbide and gallium nitride. Just to illustrate that, this chart looks at the effect of increasing the switching frequency of a power converter on the power quality input filter of that power converter, and shows that as you increase the switching frequency, the filter drops a long way in size. But it also shows that the blue line there, that the increase in the losses, the switching losses you get as you make that increase in switching frequency, is very limited in the silicon carbide MOSFET compared to the silicon IGBT. And that's been a massive change for us in the last 10 years. We can now use switching frequencies which were only possible if we went to all the trouble of resonant converters and so on in the past. When we look at power converter topologies, never believe a professor who says that a particular power converter topology is the best one to use. They all have advantages and disadvantages, and they all have areas where they're better than others. And we have to be able to look at this type of table and assess different power electronic converter types, look at losses and efficiency as well, to be able to choose the right power converter for a particular application. And when we do all of that and we look at megawatt applications of power converters in aircraft applications, particularly aircraft propulsion, we begin to see that there's a trend over time of the power electronic converters getting smaller and lighter. I've shown kilowatts per kilogram here. But it depends on how we build that power electronic converter. Do we have it as a standalone box and everyone insisting that we put our power electronics in a nice box that can be bolted into the aircraft? Or do we highly integrate the power electronics with the electrical machine and its load and make a combined package? And if we do that, if we go for that high level of integration, we'll find that the weight of the power converters becomes very small compared to today. I've shown it there going up to 250 kilowatts per kilogram. I really believe that's possible when power electronics becomes highly integrated with the electrical machine and application. Final thing I just wanted to pick up on, I mentioned earlier that flight with electric propulsion is not going to necessarily use batteries for long haul flights immediately. Maybe short and regional will do in the next 10 years. But when we look back in history, we see that battery technology evolves and changes with time. We all know of lead acid batteries, had nickel metal hydride, nickel cadmium batteries, and then the lithium technologies we have today. Where we want to be is up there with the gas turbine technology. What I predict will happen is that there will be another battery chemistry. History tells us it's there. When we get that, we will be closer to that gas turbine in terms of the energy density we can get from electrical energy storage. You'll know when this happens because you'll be charging your mobile phone once a week, not once a day, and we will be able to fly on battery technology. Where that electrical energy comes from is another story. So, just to conclude, the electrification of transportation is happening, particularly in cars, but also in aerospace. So we're seeing the reflection of automotive as well as the aerospace sector. Electrical energy storage has to improve. Power electronics and electrical machines are the key technologies, and the electrical power networks will have to have significant investment in the distribution and generation of renewable energy to make all this happen, the technologies that Freddie was talking about just before me. So thank you very much for listening. I believe that I now hand over to Samir to give the third talk.